Hello everyone. In this video, we'll go over some properties of cost functions. And this segment should look very similar to how we looked at properties of expenditure functions in the consumer theory. So let's get started. Cost functions are homogeneous of degree 1 in input prices. So what do we mean by that? If all of the input prices are doubled for a certain level of output, your cost minimizing bundle will actually be the same, except that it will now cost twice as much. Remember that when all of your prices are changing, the ratio of any two prices is not going to change. So the slope of your isoquant line won't change. And therefore, where you identify that solution of cost minimizing bundle, that point will also not change. The only change is that that bundle will now be twice as expensive because all of the prices have increased in the same proportion. And therefore, whenever you have, that's why we say that total cost functions are homogeneous of degree 1 in all the input prices. The second important property is that it is non-decreasing in Q, V, and W. By non-decreasing, what I mean is that the change in costs for any increase in Q, V, or W will be greater than or equal to 0. It will never be lesser than 0. So think about it, right? If there is any increase in the output, if you are producing more output, if the V and W doesn't change, to produce more output, you need to buy more of the inputs, right? And that should push your costs up. Unless if you're operating at an extremely, at a scale where just for a tiny increase in output, you can just manage with the inputs you have, then maybe your costs won't change overall by a huge amount. So whenever your output goes up, your costs will have to increase, provided you were operating at that optimal point to begin with. Now, suppose if it turns out that when you increase your output, your costs actually start falling, then it means that you are not optimizing to begin with, right? You should have just been producing a higher level of output because it was cheaper to do so. So naturally, so that's where the condition comes that if you increase your output at all, and if your behavior is one of optimal decision making, then greater output will increase costs. A similar rationale for how input prices will also change your costs. So suppose the cost of labor goes up. And so because one input is now expensive, you decide to switch or substitute inputs. If it so happens that even after you've switched inputs, suppose if labor is more expensive, you decide to get more capital in place of that labor, and that resulting combination of labor and capital is now cheaper, then that again tells you that you weren't optimizing in the first place. So if you're optimizing, if there's a change in Q, V, or W, your costs will either be the same or in most cases, they'll go up. Another feature, piggybacking on the previous point, is that keeping everything else constant, keeping the level of output constant, keeping the price of, say, capital constant. If suppose one input's prices are changing, let's say the price of labor keeps changing. Well, if labor is becoming more expensive, it's not going to be the case that we'll always continue to hire the same units of labor in order to produce our output. If one input just keeps becoming more and more expensive, we'll probably change our input mix. We'll maybe substitute capital in place of labor so that our overall cost comes down and we're still able to achieve our goal. So how do we describe this mathematically and graphically? Suppose our cost function is given by the concave function seen in the chart here, where the price of capital is, say, fixed at W or W prime. Our output level is fixed at Q naught. The price of labor, my apologies, I said capital. So the price of labor is initially at W prime, and this is where we are. Now, if the firm continues to use the same amount of capital and labor, but the price of labor is increasing, okay, then the costs are just going to increase in a linear manner. same amount of capital, same amount of labor, but it's just paying more per unit of labor. So your costs will climb in a linear fashion. If it were to do so, my cost function will be that part of the straight line that I've highlighted. A similar reasoning for what will happen if your wages are falling. If your one input becomes, if the wages fall, you'll go down in the other direction. But in reality, we don't actually get onto that linear line because we're going to have some input mix changes. I'm going to substitute the expensive input away and bring in the cheaper input. So my overall increase in costs will not be as much as that straight line, but it'll rather lie below. Okay. And that's where you get that concave part. Your cost function doesn't climb up linearly, but rather becomes concave because you sort of subdue the increase in your costs by switching your input so that you are producing at a lower cost. And that's why we say our input function, cost function is concave in input prices. So we've been speaking about, so a couple more properties and then we'll get into the next topic. This is again very mathematical, so and it's fairly straightforward to follow. Whenever we know that cost functions are homogeneous of degree 1 in input prices, and that property carries over to the AC and MC functions also. So when you have cost functions which are homogeneous in input prices, then if I change my input prices by a factor t, if I'm using t times, if my input prices go up by a factor of t, then my overall costs will also change by the same factor t. So that's homogeneity. Now, if I go ahead and actually write down the AC and MC functions for this particular case, turns out your AC and MC functions also exhibit homogeneity. So if I use T times V, if the price of inputs is TV and TW, your average cost is just T times the original average cost. Same for MC also. So this homogeneity property holds. But if we're talking about the how costs will change with a change in Q, V, and W, all the features, all the arguments of the cost function, that is a little bit ambiguous when you move to the average and marginal costs. Now, whenever your output is increasing, the more output you're producing, the more it's going to cost you. And it makes sense to see that your average and marginal costs will also increase when your output is going up, especially when you're in the convex part of your cost curve. So especially if you get to, this part of of your cost curve where costs are increasing rapidly, then when your output goes up, your average and marginal costs will go up. When you have when you're in the concave part of your curve, they'll be increasing, but they'll be positive, but they'll climb up when you get into the convex section. Now, your average costs will climb up when the price of inputs goes up, but we can't say that with great degree of confidence for the MC, marginal cost. So this is because in the rare case when one of your inputs is inferior, if it becomes more expensive, you will use lesser of that input. And when you use less inferior inputs, your costs will actually start going down. So your MC may fall when production goes up, when input prices go up. So this is just to summarize a bunch of different properties related to the cost functions. And now we'll get into the next one. I'll probably put that in a different video, so I'll see you there.